There we go. This is me. I'm with Argonne National Laboratory. We are yet another DOE National Laboratory. We're located just outside Chicago, so I heard some questions from the folks in Illinois. It's good to have some other Illinois folks in the room. I'm going to be talking about how we identify threats, predict vulnerabilities, and assess risks. And just to reiterate a point Lisa made a few minutes ago, if you look at the asterisk on the bottom of your agenda, I'm covering natural threats and hazards as well as climate change, not cyber or man-made risks. If you have questions throughout this, feel free to raise your hand. You don't have to save them to the end. I'm okay with that. If you do want to save them to the end, we can answer your questions at the end. This is what I'm going to cover today. So an introduction to uncertainty and risk, integrating threat information into risk-based assessments, assessing infrastructure vulnerabilities. That's sort of generic for natural hazards, for climate change, for just sort of threats, hazards, and risks. But then I'm going to talk specifically about climate change impacts and some of the background context of climate change and climate science, which I think is a useful sort of common point of departure for thinking about how we identify climate-associated risks. And then I'll talk about some resources so that I'm not leaving you here with a bunch of questions, but here's some resources and places you can go to get data and information to start assessing those types of risks. And then we'll wrap up with some questions. So let me start at the very beginning. Why do we even think about risk? It's because we live in an uncertain world. And uncertainty underpins all of this. If we lived in a completely certain world, we would know what was going to happen. We would know what the consequences of those events would be. It would be very, very easy to plan for risk. We wouldn't need this concept of risk necessarily. So uncertainty. There's lots of definitions. This is a very broad definition of uncertainty. You could drive a truck through this definition. But I like it because it sort of sets the stage. It's any departure from the unachievable ideal of complete determinism. Right? We don't live in a completely deterministic world, so it's any departure. And that could be from, is it going to rain tomorrow versus is the stock market going to crash next year? All of these are uncertain questions. There's very different levels of consequence associated with those, and that's what we'll talk about here in the next several slides, is sort of systematically thinking through how we evaluate those types of risks and consequences. There's sort of, broadly speaking, two families of uncertainty. There's just what we call aleatoric uncertainty, which is just random events. There's random processes in the world, and that leads to some sort of uncertainty in whether something will occur, the timing of that occurrence, how the magnitude of that type of event or impact. And then there's limited knowledge. We just don't know some stuff about the world. We can't even conceive of what types of information we would need to know about that. So this is sort of the Rumsfeldian unknown unknowns, if you can think of that. Yeah. So to systematically think about and deal with uncertainty, we have this concept of risk. And this is a concept that's been around for a really long time, but economists started thinking through how do we systematically think about risk starting in the 19-teens, 1920s. So Frank Knight was a professor at the University of Chicago and sort of came up with the first working definition of risk as something that derives from random adverse events with probabilities of occurrence that can be statistically calculated. And so this gets back to one of the earlier questions, that we have some event, there's some likelihood that that event will occur, and we can assign a number to that. What's the probability that that event is going to occur? This has evolved over decades and decades and decades into this more modern definition of a measure of probability and severity of adverse effects of some event. And what this boils down to is that equation that Gayatri showed on her slides of risk being a function of the do I have a laser here? I do have a laser. Risk is a function of the likelihood or the probability of an event's occurrence and the consequences of that event. This is sort of the foundation of where we start to think about definitions of risk, and it has evolved from here to encompass other things like vulnerability, and I'll talk about those in the next couple of slides. But I'm an engineer and I love an equation, so if you're looking for an equation here, it's risk equals likelihood times consequence. What's the likelihood, or that probabilistic likelihood that an event's going to occur, and what are the sort of quantitatively, what are the consequences of that event. It's easiest to do when you can quantify or calculate a statistical likelihood, right? So risk, there's a 10% probability that we're going to experience some event that will equal $1 million in losses. Consequences, we usually think about those in dollars because that's an easy common value to try and translate everything into. Economists came up with this definition of risk, so maybe there's something there where they're thinking about dollars, but it's easiest when you can come up with numbers. Whether you know it or not, this concept of risk is baked into a lot of the engineering design practices, engineering metrics out there in the world. This figure on the top right is something that I pulled from the Indiana State Department of Transportation's hydraulic design manual, which they use to design culverts. Does everybody know what a culvert is? All right, great, okay, good. So we covered permeable pavement, now we're gonna cover culverts. Culverts are just big pipes underneath a roadway that carry water from one side of the roadway to another. So if you've got a creek that you don't want to build a big bridge, you bury a big pipe. And so you see these all over the transportation network. There's way more culverts out there than bridges. So they're actually really, really important. And baked into this design of a culvert, and this is just from their design manual because it had a nice table that sort of made the point I'm trying to make here, is they're looking at, all right, let's look at the functional classification of a roadway. How big is that roadway, right? So this is, you can start to think about consequence if a freeway is disrupted versus a two-lane AADT is annual average daily traffic. That's how many vehicles are on that roadway. So a really low volume two-lane road versus a freeway, the consequence of a disruption of a freeway is way worse than a smaller road. And so then you've got a bunch of different roadways in between. They're saying that for the likelihood that some sort of a flood will occur on this, whatever stream or creek or river that this culvert is carrying, we're okay with a 1% annual probability for a freeway, right? We really don't want that to happen. But for a driveway, for a two-lane road, we're okay with a 10% likelihood that there's going to be a flood on this because the consequence is much, much lower for these smaller roadways. So this idea of risk equals probability times consequence, or likelihood times consequence, is baked into all kinds of different engineering design metrics. Seismic design for earthquakes, all kinds of other building codes have risk-based design metrics in them. And this is just one example from a transportation department. Okay, so you say, this is great. We can calculate a probability, we can calculate the losses from this, but can we always do that? Can we always say what the probability of an event is going to be? And can we always come up with a numerical, quantity of losses in dollars? We can't always do that, and so in addition to these quantitative approaches, we have qualitative approaches. And that's what this figure on the bottom is getting at. So this is from I think this is Washington State Department of Transportation. They did a climate change assessment, 2010 maybe, I think is when this figure came. And they came up with a risk matrix. And a risk matrix is a really good tool when you can't come up with hard numbers for a likelihood of event or the quantitative consequence of that event. And what they did is they got a bunch of experts together from across the Department of Transportation, and they sat them down in a room and they said, all right, let's look at bridges in our network. Let's look at highways. Let's look at overhead signage. Let's look at all of the different physical assets that we own and sort of say, where do they fall in this matrix, right? If it's a freeway bridge in downtown Seattle, because this is from Washington, remember, right? The impact of something there could be catastrophic, and depending on what type of event we're talking about, is it a hurricane? Probably not a hurricane in Seattle, so very unlikely for likelihood. Is it an earthquake? All right, well, an earthquake's probably a little bit more likely, so let's see where we feel comfortable as a group of experts saying it's, medium likelihood, likely, or very likely. And so you can go through all of the different types of hazards, all the different types of assets that you're trying to evaluate, and using a common metric like this with a bunch of experts, a bunch of smart people in a room, you can come up with this sort of qualitative approach to assessing risk. So just because you don't, the takeaway from this slide is, just because you don't have hard numbers does not mean you can't do a risk assessment. There's these types of qualitative approaches that can still be useful. And so, because of this, over time, we have developed different types of standards and frameworks. And so this is one that's very generic. This is an ISO standard, ISO 31000, and this is risk management guidelines. And this is sort of a broader risk management process that is generic for infrastructure owners and operators, for the financial sector, for business. It's just trying to come up with a very high-level way of thinking about risk systematically. And the risk assessment piece that we're talking about here today is sort of this risk identification, risk analysis, risk evaluation. So it's this middle part. You know, the scoping context, that's all important. How you treat those risks, that we'll talk about that later today. A different presenter will talk about those. But it's really this risk analysis part, these 3 steps and these 3 middle chevrons that we're talking about today. So I'd encourage you, ISO does not make this free. They make you pay for this, but it's worth it. It's like $250 or something like that. I think it's money well spent if you're looking for a good definition, a general definition of risk. But also you can get these figures for free on the internet if you look. So this is great. This is sort of a generic high-level risk management process, and that has been translated into specifically the infrastructure sector, the built environment, through additional models. This is called a catastrophe model. This is something that the insurance sector loves to use, but I think it's a really, really helpful way of fitting together these different concepts in a way that is applicable to something that is physically out there in the environment, whether it's a substation, a roadway bridge, a building, a physical asset, and thinking about how different threats and hazards affect that, and then thinking systematically about how to evaluate those. So, this figure talks about hazards, inventory, which is physical assets out in the world. There's that term vulnerability, we'll talk about that, and then loss, and that's that sort of consequence. And these are 4 words that are in this model, but there's, in these blue clouds, you're going to see lots and lots of different terms out there in the world used somewhat interchangeably. So for hazards, you'll see the word hazard. You'll also hear threats. You'll hear impacts. You'll hear risks. There's a lot of things that Gayatri talked about in her presentation. For inventory, you'll hear about infrastructure or assets or facilities or equipment. That's the type of stuff that we're thinking about there. Above vulnerability, these are not necessarily interchangeable terms, but these are what we'll talk about in a couple slides, is the 3 components of vulnerability that you can systematically and quantitatively evaluate. So that's the exposure, the sensitivity, and the adaptive capacity of an asset. And then something that I'm not going to talk about at all, but Pete Larson and some folks from Berkeley are here who will talk about consequences and sort of systematically thinking through the loss component or consequence. Okay, so let's start by talking about some hazard information. When we're thinking about hazards, broadly speaking, there's 2 ways to do this. There's probabilistic versus deterministic hazard information. And probabilistic gets back to that I can assign a likelihood to an event. I can say that there is a certain likelihood that this event will occur every year, or that will occur at some point in the future. Have you guys heard this term, say like a 50-year rainfall event or a 50-year flood? Show of hands. Okay, great. That is a probabilistic metric. What that is, and this is what we call a recurrence interval or return period. That is saying a 100-year event has a 1% annual likelihood of occurrence. And what that means is within a 100-year period, we would expect it to happen in one of those years, right? So 1% likelihood. A 20-year event has a 5% likelihood. We would expect it to happen once in every 20-year period, or 5 times in a century. So it's a 5% likelihood of occurrence, annual likelihood of occurrence. And I think that, especially with climate change, believe me, I hear this a lot. Hey, that 50-year event, is this still really a good metric? It was just a communication strategy to take a annual likelihood of occurrence and translate that into a term that someone other than a statistician would be able to make sense of. But at its heart, it is a probabilistic event. And so this figure on the right, I can't remember where I got this. Maybe this also came from Indiana. Anyway, this is showing the discharge of a river. So how much, this is CFS is cubic feet per second, so how much water flows through a river and has return periods. So for a 1.5-year event, right, like this is almost an annual occurrence, right? We have about 4,000 cubic feet per second of water flowing through this river. If we go to that 100-year event, we're almost at 1,000. And this is key because the way that we arrive at these probabilistic likelihoods is through historical observation. So each of these points represents a measurement from a stream gauge in this river that's been out there for decades or a century, recording every year what was the maximum sort of amount of water that, that flowed through that river. And so we can stack that up over time and create these types of probabilistic metrics. As we'll talk about in a few slides with climate change, it becomes difficult to do because our historical observations are no longer a fair representation of what we can expect to occur in the future. So we'll talk about that in a few slides. Has everybody heard of FEMA flood maps? Show of hands? Great. Also a probabilistic-based metric. So FEMA puts out their 100-year floodplain, their 500-year floodplain. This is a figure, this is not one of their maps, but the data that we put into this GIS software is from FEMA. The light blue is a 100-year coastal floodplain. And sort of this dark blue fringe is the extra area that was covered under a 500-year flood. So 100-year floodplain, that has a 1% likelihood, annual likelihood of occurrence. The 500-year floodplain has a 0.2% annual likelihood of occurrence. So again, a probabilistic hazard information that's already out there in metrics that we're, or tools and data sets that we're already familiar with. So, deterministic information. Sometimes you can't always come up with a probability for the likelihood that an event will occur. And this is oftentimes when we don't have enough historical observation. And earthquakes are a good example of that because they happen so infrequently. And it's not until more modern times that we've had really good tools and instruments to measure where they're located, how severe they were, their characteristics, where they spread. So what we really look at here are deterministic approaches, which is to say we look at individual scenarios. We're not looking at the likelihood of an event. We're looking at a specific event as it's envisioned that it may occur in the future. And so these are maps from the USGS, the US Geological Survey, for an earthquake in the Willamette Valley in Oregon. And we have two. There's one that's sort of centered down here halfway between Portland and Salem, which is the state's capital. And then we've got another one closer up to Portland, Oregon here. If you looked at these two maps, and this is sort of one of the shortcomings of this deterministic-based approach, if you look at only one of these figures in seismic planes, say you're designing a bridge, you're designing a substation, you're designing a building, if you only look at the one on the left and you're building a building in Portland, you might think, oh great, we're actually in a pretty good spot here, right? Like the earthquake, the greater risk is down down towards Salem. Whereas if you only looked at the one on the right, you'd say, oh, man, there's a really, really bad earthquake probability up here, or earthquake that could occur. Maybe we're going to design a building differently. So what we see is over time, to do these types of analyses, instead of looking at a single scenario for that deterministic-based approach, folks start looking at larger numbers of scenarios, or we talk about ensembles of scenarios. And so this kind of bridges the gap between that probabilistic and that deterministic approach, and so this is the map online. If you click on one of these, you get one of these figures. But the sort of the summary map, which is for the entire region, is this one, which shows all of the different earthquake scenarios that are projected across Western Oregon. And this paints a very, very different picture, but it starts moving towards that probabilistic-based approach because we just have lots and lots of different examples that paint a more complete picture of the risk. And basically what this says is if you're in western Oregon, sort of to the left of the Cascade Mountains, which run north to south right here, like, it's pretty consistent seismic risk across the state. Whereas if you looked at only one of these figures, you think, all right, well, it's only in certain spots where I have these problems. So that's one of the trade-offs with this deterministic-based approach, but when you don't have lots and lots of historical record, this is the type of thing that we're forced to do when evaluating threats and hazards. Okay, questions so far? Okay. So now I want to talk about vulnerability information. So this was, you know, I think we'll respond to one of the questions from the previous presentation. We can systematically think through vulnerability. And to do this, I like this definition that breaks vulnerability down into 3 different components. And these are components that we can, if not completely quantitatively measure, we can do a pretty good job of qualitatively measuring them. This definition of vulnerability says it's a function of exposure, sensitivity, and adaptive capacity. In one of the previous training sessions we did, someone said, gosh, is it really like plus and minus? I saw it was plus and plus in another presentation. Let us not get too wound up about the pluses and minuses here. Let's just say vulnerability is a function of these 3 different components. And this is a definition from the IPCC, which is part of the United Nations. This is the Intergovernmental Panel on Climate Change. And so this is sort of their underlying definition of vulnerability that they use to think through climate risks and hazards, but I think it's very broadly applicable when thinking about vulnerability. And I want to talk through each of these components here: exposure, sensitivity, and adaptive capacity. So let's talk about exposure first. Let's go back to Oregon and talk more about earthquakes in Oregon. I did a project in Oregon that was with the Department of Transportation looking at the seismic vulnerability of bridges and roadways across the state. The map on the left this is a single scenario, so this is a deterministic analysis. This is for what's called a Cascadia subduction zone earthquake. The Cascadia subduction zone is this massive, massive seismic region that runs from Canada, from the north end of Vancouver Island, all the way down to Northern California. And it's one massive fault line that if that thing goes, it's going to impact not just Oregon, but Washington and Northern California as well. And so what you see is the darker shading is the stronger seismic shaking, right? And it sort of diminishes as you go across the state. And the state was really concerned about what does this mean for bridges sort of at a state level. And so the figure on the right maps out all of the bridges across the state. And if you add these 2 together, you can create this new map that shows the exposure of each of those assets to this hazard. What this says is that, and so I've color-coded them here. If it has higher exposure to stronger shaking, it's in red, generally in the western part of the state. And if it's green, it's over here in the right-hand side of the state and is exposed to lower shaking. What this means is, as the State Department of Transportation, for example, is trying to think through where should we spend our money to seismically retrofit our bridges, it doesn't make as much sense to go over to Pendleton or some of these cities on the eastern side of the state when really the greatest hazard exposure for this one earthquake scenario, admittedly, is on the western side of the state. So it's not to say they shouldn't look at bridges on the right-hand side in the eastern part of the state for other reasons. It's really saying that if you're concerned about seismic risks in Oregon, we can basically ignore half of the bridges across the state and focus our energies on bridges in the western part of the state, right? So that's looking at the exposure of these types of assets. And the same thing happens for other types of hazards. So again, I'm in Illinois. I'm not really concerned about our exposure to hurricane impacts because that's not the type of natural hazard that occurs in Illinois. If I'm in Florida, I'm thinking about that very, very differently, about the exposure of my assets to hurricane impacts. So sensitivity gets into just because it's exposed. Do you have a question? Yeah.
On the previous slide, so does it make sense at all to invest into the red zone? I'm sorry. Again, sorry. Does it make sense at all to invest into the red zone bridges? Because
we expect an earthquake to be really strong, right? So the red one's gonna most probably go, right?
That gets into, yeah, it's like you're setting up my next slide perfectly, because the answer is, of course, it depends, right? And that gets into the sensitivity. Just because you're exposed to some sort of an impact doesn't mean that every asset is equally sensitive to that. I could have a brand new bridge in Portland, Oregon that was built to the latest seismic design standards, right? That is brand new, and it might be able to withstand an extremely strong earthquake like a Cascadia subduction zone earthquake, which is a magnitude 9.0 earthquake. Like, this is a really strong earthquake. The characteristic, just because it's interesting real quick, they're projecting 2 to 6 minutes of shaking in a Cascadia subduction zone earthquake, which, like, if you think of the earthquakes in California, which are shallow crustal fault earthquakes, that's like 30 seconds of shaking at most, which feels like an eternity. I lived in Seattle when they had the Nisqually quake in 2001, which was 20 seconds, and I was in high school, but it was like 20 seconds is a long time for the earth to be shaking. So 2 to 6 minutes would be terrifying, but also really destructive for infrastructure. But for a brand new bridge, that may not be a problem. If you have a 100-year-old steel plate girder bridge on the coast of Oregon that hasn't been seismically retrofitted, that could be a very different problem. And that gets into the differences in sensitivity of these different pieces of infrastructure to the types of hazards to which they'll be exposed. Even if they're in the same spot, they could experience that type of hazard differently. And so this is one example, which is I'm trying to get away from earthquakes and give you something else. This is an example of flooding. This is from, I think this is from Georgia, actually. And what we see in this figure is there's a flood. There's two types of infrastructure in this figure. There's a roadway, and then there are some power lines. And they're both exposed to a flood. The roadway is completely disrupted by this flooding event. And I don't know for certain, but I'm pretty sure that these power lines are still energized and still working perfectly fine. They both experience the same exposure to that flooding event, but have very, very different levels of sensitivity to that event. And sure, you could say, all right, well, if this flooding was prolonged and these are wood poles, maybe there's something to the degradation of the wood if they're soaked in water for days or weeks or months. But generally speaking, for these more short-term types of impacts, very different exposure. Now, if it was a substation here, that's also an electric asset, but that would be located on the ground. Maybe that would have a different sensitivity to a flooding event occurring at the exact same location. And the good news is, and I think this gets maybe to one of the questions earlier about quantitatively thinking about vulnerability, is that there are ways that we can quantify and sort of systematically look at sensitivity of assets. And something that we commonly use at the National Lab, that this is actually, this isn't from FEMA, but FEMA has a model called the HAZUS model, which has lots of these. This is a fragility curve. And so fragility curves are similar. Sometimes you hear them called performance curves, but the idea here is that we have some sort of an event with a certain amount of intensity, and then we have the likelihood that type of asset will fail as a result. And so in this figure, we have transmission towers and transmission lines, and this is weather intensity. This is wind speed, is what this figure is showing. And so if you have a wind speed of about 100 meters per second, well, there's maybe, we'll call that a 50% failure probability for the transmission tower. But at 100 meters per second, you're already at 100% failure likelihood for your transmission line. So that tells you a little something just about differences in sensitivity between transmission towers versus transmission lines here, but it's also a way that we can more quantitatively think about how sensitive these different types of assets are to, in this case, wind, but these fragility curves exist for all kinds of different types of natural hazards. And if you're thinking about evaluating a natural hazard on your system or in your area and a fragility curve doesn't exist, call up your local university, because this is exactly the type of stuff that structural engineering professors and their research groups develop. I've worked with some professors at Iowa State University who do this type of work, and they've helped us out on a lot of projects. Okay, so adaptive capacity is probably I think the most nebulous of these, and it's not something that we can quantify quite as readily as the other two. But let me go back way, way in history for an example, because although the concept is new, in practice, it's been out there for a long, long time. And adaptive capacity is effectively the ability of a system to adjust to changes, manage damages, take advantage of opportunities, or cope with consequences. These are two bridges in Italy that the Romans built, and they are good examples of adaptive capacity. What both of these bridges have in common is they used to wash out frequently, and so the Romans used to have to rebuild these bridges with some frequency in order to traverse these two rivers. And at some point, some Roman engineers said, hey, why don't we add these little openings in the bridge piers so that as floodwaters rise and they impose lateral forces on our bridge piers, which is what's causing these bridges to wash out, if we put these little openings here, then water can flow through the bridges. And it puts less lateral loading on the bridge piers so that the bridges don't wash out. And as evidence, these bridges are still standing today. So it worked. This is what I would call a static adaptive capacity strategy. Nothing has to change. No one has to go out there and turn a lever or do anything. It's part of the design of the bridges that they are adapting in real time to those rising floodwaters. When the rivers are at their lower levels like they are here, everything's fine. The bridges are functioning as normal. These openings don't do anything. They're maybe just a pretty architectural feature. But when the floodwaters rise, this bridge is sort of adapting to those changing conditions. And so it's a part of the baked-in design of this bridge. We also see adaptive capacity through more of a dynamic type of sense with disaster or demand response events. So this is an example from NISO, where you have projected demand was going to outstrip actual generation capacity. And so they initiated a demand response event and said, all right, to their large C&I customers, hey, can you dim the lights in the lobbies of your hotels? Can you, grocery stores, turn up your freezers by 1 or 2 degrees? So everything's still fine, you're still functioning just fine, but you're consuming just a little bit of electricity. And across these large C&I customers, if they all work in aggregate, they can artificially lower demand just a little bit so that it doesn't exceed generation capacity. And that is a dynamic, adaptive action that can be taken in response to these types of projected events, and is a really good example of adaptive capacity for, in this case, a large power grid, not just a single individual asset or something like that. Okay, so Tom, you've been talking about risk a lot, but we're here to talk about resilience as well. So where does this concept of risk and concept of resilience sort of work together? And Gayatri talked about this a little bit in her slides. There are lots and lots of definitions of resilience out there in the world. And I don't want you to get the idea that any one of them is right, but I do want you, they're all useful, and they all have a lot in common. And if you look at all of them, they have these 4 words or some permutation of these 4 words in them. And that's the key here, is that resilience is the ability to prepare for something, to adapt to something, to withstand something as it's occurring, and to recover rapidly. It's not worth getting too wound up in the definition, but these concepts are really the key to resilience. And this comes from Presidential Policy Directive 21, which is what Gayatri also referenced, and I think is sort of a common foundation that a lot of people try and build an improved definition of resilience off of. But I'm here to tell you, if we all come back to sort of these 4 basic components, we're in pretty good shape. So we can systematically think about resilience, just as we systematically think about risk. And this is what's called a resilience curve. Sometimes you hear it called a bathtub curve. Gayatri showed a version of this in her presentation before mine. But the idea here is that you have some sort of service. This is, I think, communication infrastructure. So let's just say it's a telephone network. And you have, as you go through time, some event occurs. I think Gayatri, she framed it as, what was it, action versus response in her slides? Anyway, there's a guy that I work with at DHS who is a former Army Scout platoon leader, and he thinks of this, he calls this event boom. And he thinks of everything to the left of that as left of boom, and everything to the right of that as right of boom, and you have some sort of disruptive event that is your boom event. So we have left of boom, everything is in your telephone network is working fine, and then you have some sort of a disruptive event. That could be a natural hazard, could be a cyber attack, could be some other type of impact, and you have a degradation in service. Some people aren't able to get to pick up the phone and make a phone call. Over time, you recover from that and get back to your service as it was previously before the event, when you were left of boom. I put the concepts of resilience over here, these sort of 4 elements: prepare, adapt, withstand, and recover, and they map onto this very, very well. There's actions that you can take before an event to be better prepared. That might be better response planning. That might be better planning for capital investments into the system to make it stronger, to make it more resilient. There's things that you can do in engineered systems through design, through management practices to make them better able to withstand some sort of a disruptive event. And what you're trying to do there is make this sort of drop in service less sharp. Maybe you can cut that in half. You can withstand more and more of the event. How you recover from the event. What are your response and recovery practices? Can you make the slope of this line steeper, which effectively means you recover more quickly and get back to your previous level of service more rapidly? And then what can you do? Looking back and saying, well, we can learn from this event. What can you do to adapt into the future so that maybe you have different management practices, you update your designs, you update your building codes so that you're better prepared next time. And if that sounds a lot like preparation, it's because it all kind of loops back to before the next event occurs, right? I didn't put it in this presentation, but there's a figure I like from a research group at Georgia Tech where they show a bunch of these lined up. And you have one event that goes into the next event, that goes into the next event. And different strategies over time that can change the shape of this curve so you don't have quite as strong of a disruption, you recover more rapidly. But it is really that adaptation kind of turns into planning for the next event. Okay, so this is sort of a break in my presentation. I'm going to now move on to talk more about climate change impacts. And I have 15 minutes? Okay. Plus Q&A. Okay, cool. We've been kind of covering a couple questions as we go, so maybe I've got a couple extra minutes. All right, so I want to talk just some basic climate science and modeling 101. And so I guess just for context and continuity in the presentation, right, all of the concept of sort of assessing threats, vulnerabilities, and risks from natural hazards apply to climate change as sort of a subset of those types of natural hazards, threats, and risks, but we have to think about a couple things a little bit differently. So I put this figure up. Are people familiar with these graphs? Have you seen these before? Okay, so fewer hands than had heard of culverts. I don't know, maybe that's a good thing. So what these figures are showing, these are also from the IPCC, the Intergovernmental Panel on Climate Change, and these are showing greenhouse gas emissions, or no, I'm sorry. The figure on the left is showing greenhouse gas emissions into the future. And then the figure on the right is showing what those effectively mean for average surface temperature across the globe. And so what you see is these sort of conceptualizations of how we may diminish the amount of greenhouse gases that we're emitting to the atmosphere into the future through the end of the century, or we have sort of this worst case scenario where we continue to emit greenhouse gases into the atmosphere well towards the end of the century. We talk about this as sort of the business as usual case because it's how we've been doing things for decades and decades and decades. Each of those have different implications for what will happen. Sort of, you can think of global surface temperature as sort of an overly simplified metric for how bad, what does this mean climate change will be. And the key to this slide, and the reason I put it up here, is that the IPCC, which is a collection of the world's greatest scientists and minds thinking about the future of climate change in the world, they don't assign probabilistic likelihood to any of these. They say any one of these scenarios is just as likely as another scenario. Now, having said that, I don't feel as optimistic that tomorrow we're going to flip a switch and immediately start reducing our greenhouse gas emissions. So although I can't say there's a lower likelihood or lower probability for these two blue lines, I don't feel as good about them into the future. And so I feel better. I don't feel good, but I feel maybe better is the wrong word, but with these types of lines into the future because I think that they're maybe more realistic. But because there's no probabilistic likelihood assigned to any of these scenarios into the future, that really complicates how we think about risk, right? So we can't think about probabilistic likelihood. We now need to start thinking maybe more of that deterministic approach that we talked about. So to translate those types of emission scenarios and sort of how humans continue to emit greenhouse gases in the atmosphere, what does that mean for local types of impacts? To do this, we look at climate change models. And so a climate model, a global climate model, is just a massive, massive computer model that is a bunch of equations that model all of the different processes in Earth's atmosphere, in terrestrial systems, in land systems, in oceanic systems, and model all of the different interactions between these systems to show how climate will evolve as we step through time. What this looks like in a model is I like to think of sort of a checkerboard laid across the globe, and within each of those grid cells you have all of these bunches of equations that are modeling for each grid cell all of the climatological processes and environmental processes that affect climate. And we step through time and all of those calculations in every single grid cell updates. We can step through time in a matter of seconds. We can step through time as updating in a matter of minutes or hours. But we're stepping through time to see how climate will evolve into the future. And realistically, it's a three-dimensional checkerboard or chessboard at this point because we're also looking at different layers of the atmosphere. Over time, these models have gotten better. And one of the ways that they've gotten better is our computers have gotten faster. And so all of the amount of, our ability to calculate all of the equations in each of these grid cells is limited by how quick our computers are because there's so many computations that have to occur. So we talk about the spatial resolution of these models as the size of these checkerboard squares, the size of these grid cells. And a global climate model, these checkerboards, these grid cells are about 100 kilometers by 100 kilometers, so they're pretty big. Right? A lot can happen in 100 kilometers by 100 kilometers. So that's saying, if we just look at the state of Florida, that's maybe a dozen grid cells for the entire state of Florida, which means if we're trying to look at how climate will impact a piece of infrastructure, that's not very specific, right? That's saying what happens on the north side of Miami and the south side of Miami or on the coast versus inland is the same. And we know just from experience that it can be highly variable across these smaller regions. But as computers have gotten faster, we've been able to shrink down the size of these grid cells smaller and smaller and smaller, which allow us to look at more and more specific locations and how climate change impacts will manifest differently at much, much smaller and more specific locations across a region. So there's two different types well, let me back up and say, this whole process of going from higher resolution, or lower resolution, so bigger grid cells down to smaller grid cells, is called downscaling. So we've got these global climate models that look at global climate trends, and we have these other types of activities that take those large global scale climate models and downscale them to very, very local types of impacts. There's two different ways of doing this. There's statistical downscaling, which is just based on more mathematical models. And there's dynamical downscaling, which is looking at building, instead of a global climate model, building a regional climate model of a smaller area. The figures on the right are a regional climate model that we at Argonne have built for North America. So this is great. Instead of taking the same supercomputer and focusing it on the entire globe, if we look at just North America, we can have a greater number of smaller grid cells with the same amount of computing power. And I like to think of this as, like the screen on your cell phone or a digital camera or something like that. If you have a greater number of pixels in the same area, you get a clearer picture. And it's the exact same idea with climate models. And this figure actually shows, sort of the blurrier picture of a global climate model versus how that gets translated or downscaled into much more higher resolution, more location-specific types of climate impacts. Same underlying data, same events, but you can see a lot more detail in the figure on the right. What does this look like in practice? So the figure on the top right is a global climate model grid cell for covering New Jersey and sort of metropolitan New York City. The figure on the bottom is the same area, the same data, in fact, for but from a 12-kilometer regional climate model. And so you just see a lot more, right? If you were trying to generalize climate impacts in this grid cell, you'd get close, right? But you get a lot more detail, a lot more variability across the same region with this more detailed model. And so this is a 100-kilometer by 100-kilometer grid cell. These are 12 by 12. And right now we're working to try and enhance that to 4-kilometer by 4-kilometer. And there's efforts elsewhere to even push beyond that. We're not going to talk about it today, but like the sort of the proliferation of artificial intelligence and machine learning based tools over the last couple of years, I think is really going to accelerate this so that we can get to even more local scale impacts. Okay, how am I doing on time?
You have about 20, well, maybe 5 minutes.
Yeah, okay, that should be okay. So I want to leave you with some resources. Because there's lots and lots of climate data out there, but it's difficult to know where to get like sort of systematically good types of data sets that are tailored to these types of use cases. So this is a tool that we developed at Argonne. This is with the data from our climate model, but we're looking at other types of data sets that we can integrate into it. We call it Climber, or the Climate Risk and Resilience Portal. We developed this sort of as a joint collaboration between Argonne, FEMA, the Department of Energy's Grid Deployment Office, who's helping put on this event today, and AT&T, sort of as a large national infrastructure owner and operator. And the URL is here, so you can pull it up on your laptop. It works okay on your cell phone, but it's going to be a better experience if you do it on a laptop browser. And you have options to look either at national maps. This is a wildfire risk map. I don't want you to get too scared. This is a historical wildfire risk map, so this is like what it's already looked like across the country, but we have future wildfire risk as well. You can also type in a street address. You can type in a point of interest, so you could type in the Grand Ole Opry and pull up on a map and see, all right, well, what are the local climate impacts at that location? For this figure on the right, I typed in Argonne National Laboratory, and this is the 12-kilometer by 12-kilometer grid cell from our climate model that covers Argonne. And then below that is a summary of all of the different types of historical and projected future climate impacts at that location. So if you're trying to look at the impacts at a specific substation, you can enter the street address for that and get a summary report of that. If you're looking at how will it affect a small campus or another type of facility, you can do that as well. This is another great tool. This was created by NOAA. This is called CAMERA, the Climate Mapping for Resilience and Adaptation Assessment Tool. So the CAMERA assessment tool, this uses a statistically downscaled data set. So Argonne's data is dynamically downscaled. This is statistically downscaled data. It's aggregated mostly to the county level, but whereas our data set has a lot of detail at a local scale, sometimes you just want a county level summary of what our climate impacts looking like across a region, and the CAMERA tool does a really, really good job of that. They built in some easy bar graphs. This is actually something that we stole from them and put into our portal as well in a recent update to it, so that you can have some quick bar graphs to look at historical versus future types of impacts across a region. Both of these use data sets that are widely peer-reviewed and widely published. So I mentioned both of them because I think they have very good scientifically defensible data behind them. There are some state-level efforts afoot that are also introducing similarly great data. This is a tool called CalAdapt. It's mostly for the state of California, but as you can see, the data covers also most of Nevada, which they've done just because climate models are very squared off grids. So to model all of California, they captured most of Nevada as well. Is anybody in the room from California? Okay, all right, we got one in the back, great. I put this slide in here because this is a really great tool with a lot of advanced analysis in it that the CalAdapt folks have created, working very closely with the utilities across the state, with Southern California Edison, with PG&E and others, to do an even better job of understanding what a utility specifically needs to know about future climate and then building that into their tool. So I'm not going to spend too much time on these slides just in the interest of time, but I will say this comes from a study that we at Argonne did with our local distribution utility, ComEd, in northern Illinois. And I'll just point out, I think you've got access to these slides. These tables came from, if you go to this URL, you can download the PDF of the study that we did with ComEd. it has a series of tables in here that sort of identify different ways in which electric and power grid assets are vulnerable to different types of hazards. And so we have more on the distribution side, we have distribution poles. How are they affected by extreme cold, by wind, by flooding, by increased stream flows in rivers, by ice, by overgrown trees and vegetation? And all of this is from a massive, massive literature review. So it's not us saying it because we sat down and thought about it. It's looking at sort of a bunch of vulnerability studies that have been conducted across the country and trying to condense that down into one table. But I put on the right some figures showing things that we don't always think about, right? We think about extreme cold. I think icing is probably fairly familiar to most utilities, but things like snow on solar panels, right? If we're trying to have a greater amount of distributed energy resources out in the power grid, right? Snow can affect a solar panel. If it's completely covered, it's not generating electricity. This figure is actually from a pilot study that DOE was doing where they're applying coatings to solar panels to make the snow slide off and not accumulate. So there's some strategies to overcome this, but it's something worth considering and thinking about more broadly about how climate change and changing weather can affect our power grid. This is one for more transmission types of assets, so transmission lines, structures, transformers. This figure on the left shows obviously a flooded substation. So it's a pretty massive substation to be impacted by a flood, and starting to think about, well, what could we do differently? Like maybe it's elevating key components of this substation, maybe it's trying to shift load to build another substation elsewhere or expand a substation elsewhere so that we can shift some of the load to that substation. There are other ways that these substations could be affected, so that's what these tables get at. And then we also cover a little bit about generation and gas lines in here. So, I put some figures or some values here, again, getting back to that quantitative risk assessment from a study that the California Energy Commission did, that as it gets hotter, our power plants aren't able to cool as efficiently, and so they can't generate as much electricity. It turns out the transmission grid can't transmit that electricity as efficiently when it's hot out. And there have been some studies that start to put numbers to that. So for every degree Celsius increase in temperature, our average transformer output decreases by about 1%. So, all right. There's a ton of material, and I've been racing through it. So I appreciate your patience and your attention. I'm not going to go through these questions. We were sort of asked to compile a list of questions at these presentations that folks in the room can start thinking about, asking people in their regions as they're thinking about climate change and how they're responding to climate change. I was told to come up with one slide, but I couldn't put it all on one slide, so I came up with two that are roughly aligned to some of the content in this sort of overall risk assessment process, right? So as people are scoping their risk assessment projects for climate change, what's the criteria, what are the emission scenarios you're looking for? Some questions related to risk identification, right? So what are the types of hazards that you're concerned about? How are you assessing those? Risk analysis and risk evaluation. So how are you systematically thinking through how those risks and threats and hazards will affect your system? Okay. Thank you very much for your attention. Hopefully this was useful. If you guys have questions, I'm happy to take those now.